Let's talk about ion electron configuration. And so what we want to do is start with the atom's electron configuration. And for a cation, we remove the last added electrons, with the exception of the transition metals, where we have to remove the valence s orbital before we remove the d electrons. We'll do an example of that in a sec. And then for anions, we actually just add electrons to what we already have to get a noble gas configuration. So that's pretty easy. Let's start with fluorine to illustrate anion electron configuration. So if we look at fluorine and we read the periodic table like a book and we go 1s, 2s, and then 2p, we can say 1s2, 2 electrons in the 1s, 2 electrons in the 2s, and then how many in the p? 1, 2, 3, 4, 5. So we've got 2p5, and that's fluorine, the atom's electron configuration. What we do to get the anion, F minus, we add 1 electron and we get a full valence shell. So we basically move over and become isoelectronic with neon. And so we can use the noble gas configuration to show that fluorine minus has the same configuration as neon, the noble gas. 1s2, 2s2, 2p6, started with 2p5 for fluorine. Let's start with magnesium, and let's use noble gas configuration. So we have the same as up and to the right. Well, all the way to the right is neon here. And we're on 1 to row 3, so 3s2, starting with magnesium, the atom. To get the cation, we take off 2 electrons, because we know that in group 2a, those ions or those atoms prefer 2 plus ions. Group 1 prefers 1 plus. Aluminum likes 3 plus here, and so forth. So we've seen that in earlier studies. If we take 2 electrons off, we take them out of the last added, okay? And so we again have the same noble gas configuration as neon for magnesium 2 plus, the ion. But for transition metals, it is a little bit different. And so let's look at iron. Where is iron on the periodic table? There it is. Let's do its noble gas configuration. So it's argon. And then we have 4s2. And then 3d here. Remember, the 3d starts in row 4. Even though it's physically in the third shell, it doesn't fill till after the 4s electrons. And then we count them 1, 2, 3, 4, 5, 6, 3d6 for iron. Okay, and we're not borrowing, or it's not one of our exceptions like chromium or copper, so we're there for iron. Then we want to take off an electron. Here's where we're a little bit different. We take away the valence electrons first. And so because the 3 level, 2, 3, the 3 level is inside of the 4. The 4s electrons are actually valence. The 3d electrons, along with the 3s and the 3p, they are actually inner core electrons. So the easiest ones to pluck are the 2 electrons from the s. We start 4s1. Let's stay consistent here. 4s1, 3d6. And then we remove the next least shielded, the most available, is in the valence electrons again. And so with iron 2 plus, we'd end up with 3d6. For iron 3 plus, again, argon's configuration. Now, finally, the highest energy valence electrons are not the 3s, they're not the 3p. Then the 4s we just emptied. Well, the next highest energy that are left in row 3 are the 3d. These guys are already full. Okay, should only be 1 orbital there. These guys are full, and we've got 6 electrons, 1, 2, 3, 4, 5, and 6. So one of them was paired, so this one would unpair and make 3d5. So iron 3 plus has a half-filled d subshell, so it's a pretty stable ion. We see iron in all three oxidation states in molecules. Okay, but remove the valence first, and then you remove the last added d electrons from the inner core.